Great, thank you very much. Yes, thank you for the introduction, and thank you again for the opportunity to speak here. Alexi and I are very grateful to be able to share with you what we've learned and the things that we've been working on. So as it was said, we work for Altius, which is a data and applied AI consultancy, and what we're going to try and go through is a combination of the things that we've learned working on various price optimization projects. So it's not going to be a kind of a story of one from beginning to end, but various things that we've gleaned and things that we think have been insightful or interesting along the way. So the agenda looks like this. So we have kind of a linear thing that we'll go down, but like I said, it's not so much the story of one thing from beginning to end. So we'll talk a little bit about what machine learning for price optimization means, and then what that often means when you come into contact with real business and the real data situations, and how we sort of have to deal with exploring those systems. And then begin to talk into like how we begin to build and construct the algorithms to achieve a price solution for a given client, and some of the challenges that are involved around that. So we talk about kind of various encoding techniques, choices of algorithm, and so on. And then we kind of have a break and talk about problems that occur along the way and how we begin to think about solving those. And then finally going to talk about productionizing and how we move forward into providing a kind of a stable operational solution. So you can think of this linearly, or you can think of this as kind of like a Git flow. So we start out with our data exploration. We're going to add some features in around the algorithm and encoding and things like that. Then we're going to try and test it, see what things have gone wrong, some of the bug fixes that we had to deal with, and then go on to a release and think about how we're going to actually productionize this going forward. So starting out with machine learning for price optimization, when we talk about price optimization, there are kind of three things that a business is generally interested in when they're trying to optimize their price. So they might want to optimize for revenue. This means kind of they're going to keep a stable market share, but they want to make more revenue out of the market share that they already have. So it doesn't necessarily mean losing customers, and it doesn't necessarily mean gaining customers, but it's kind of increasing revenue on what they've got. So it might mean increasing price, and it might mean decreasing price as well. The second option is to optimize for profit. So this means losing market share isn't a problem, but as long as the total profit that's gained on the customers that are retained is higher. So you might want to increase price around the customers that you know you're going to retain and make more profit out of those, and not worry so much around the customers that you weren't making a lot of profit out of anyway. And then the third option is to optimize for market share, which generally means lowering the price. So you're trying to look at the regions where you could have been winning business, you could have been making sales, but you weren't successful because the price was too high, and you're going to try and lower that to see if you can capture that segment of the market. So these three sections, depending on the needs of the given business, they might have a priority one over the other, and this tends to feed in to how the data science solution is developed and what kind of algorithm or approach is going to be best suited. So we can think of this, depending on which kind of priority a given business has, it's probably going to go down three phases. So initially, when you kind of come into contact with a business, they may not have thought too much or to have too much experience around applying data science or applied AI to achieve what they're looking for. Probably have some legacy solutions. They've probably been using some kind of operational research, which has been around for quite a long time, or they may not really have any particular strategy at all. So often the pricing that is at the first stage may not be very consistent. So the first stage tends to be to standardize this. So we're going to try and take what information we do have from the business, learn from it, and then apply an algorithm which gives a standard price for that given product or for the business in general. So this is more of a standard machine learning solution, and we're probably talking about a regression problem of some kind. So we have their data set, we're going to apply a regression, learn what is important for this business going into their price, and provide a model which then gives them the price back to them. So it's standardizing in a way that they're not having any kind of random fluctuations or inconsistencies. The second phase is where the optimization begins. So this is where, in general, ideally, you'd like to learn from both the prices that have been given and the business that's been won, but also where things have been lost. So you need to know, in general, there's ways around it, but you need to know where the business has been lost to see how high a given price might be pushed, or where the price might need to be lowered to actually win that business. So as I said, depending on the particular priority, this might involve increasing the price to where the business was already likely to be won, or decreasing the price where it was likely to be lost. But in general, it's an optimization problem around revenue of some kind. The third stage, which is probably the most advanced and rarest of those, is when there isn't really any more data to learn from. So we're not kind of applying machine learning solution to existing sales data or existing kind of quote data, but we're allowing some AI solution to explore on its own. So it becomes a reinforcement learning problem where an AI agent is going to recommend a price, see if it wins, see if it loses, and then learn purely from the prices that it itself has been recommending. But like I say, that's something of a rarer occurrence. So in general, modes of working, it kind of depends obviously on who is involved, but the way we do things is tend to be, we have a combination of design, development, and data science, and then iterate between these various streams with the goal that we're going to produce a pricing solution of some kind. So this could be just an API that a customer is able to use to get the price that is generated from a model that we host, or it could be a web front end that wraps around that, and you see the website for the given business. So it kind of depends on what the needs are. And then this will feed into a various testing stream, and then based on the live testing, this will iterate back and move forward. So it's probably a kind of pretty standard software development structure around this. So moving on to data exploration. Before we kind of get into some of the details, we need to kind of give a few assumptions around what the content of the rest of the talk is going to involve. So as I said, we build forecasting and price optimization solutions for clients. So it's not an in-house product, but we kind of build these out for other people. And that means that there's kind of differences between the various products that we end up building. So there's going to be a range of scope and complexity. Some of it might be extremely complex, but we have full scope, so we build it from beginning to end. Some of it might be not so complex, and it's just one part of the solution that we're involved in. So the various things that I'll get to later, it may not necessarily generic learnings. Some of it might apply to a given situation, and some of it might be more useful for a project on the whole. So assuming that we're optimizing price for businesses that do have flexibility around that price. So they're providing a good or a service, and this price can be dynamic. There's no kind of fixed price at which they have to sell for. They have the luxury of offering whatever they like. And although there may be some considerations where we have to limit according to kind of business requirements around the outside. And the final assumption really is that there's data to learn from. So they've been recording what it is they've been selling and how much they sold it for, and hopefully whether they tried to sell it and they didn't for a given price. And there could be various other things that are involved in that structure. So there could be existing pricing tools. There could be humans involved who are just making up the price and kind of going with it on the fly. Or it could be a combination of these things. So those systems and knowledge that will be typically, when we come to kind of learn what it is we're trying to provide, is a combination of things. So there's business knowledge. This is talking to people, the salespeople that are involved, and saying, well, what is it really that drives your price? Even if it's not necessarily visible in the data, what do you think is going to be important when we want to increase the price to gain profit out of a certain sector? The second part is the existing systems. So like I said, there could be some older operational research type method where someone has developed a theory of what the price should be, and they've plugged it in, and this is what is generating the recommended prices at the moment. Sometimes that can be replaced, sometimes it has to be integrated and dealt with. Sales data, most important probably, is just the record, making sure that people have been recording exactly what it is they've been selling and that price. And this is what the machine learning solution is going to be built on, but the structure of that solution is going to be influenced by the other factors. And then finally, market research. So really, competitor information is extremely important. So we need to understand not just what the business is selling, but where it fits in the rest of the market and where it's sort of where the elasticity of its price is really being driven by. So feature types. So I'm going to say that this is the most important part of dealing with any solution, right? Because features are more important than the algorithm that you ultimately end up with. So why do I say that? I mean, choosing the optimum algorithm might get you from 95% to 98%, and doing effective hyperparameter optimization might get you from 98 to 99%, but it's not going to get you off of 0. It's not going to get you from 50 to 90%. To do that, you've got to understand what is important and driving the ultimate outcome of your model. So that means getting the features that are going to be necessary. So this depends a lot on the given business for a price optimization solution, but it's going to cover a number of pretty common areas. So product, so what is it that's being sold? Is it like fish? Is it going to go off? Or is it screws, something that's going to last forever? Is it a premium product, or is it kind of a bargain product? What are the costs involved in producing this product, and how frequently is it being sold? Seasonality, is this a summer or a winter issue? Are holidays going to be important, for example? And then geography, where is it being sold? Does that matter? Is it something that needs to be shipped from one place to another? Are the customers different depending on the geography? And are we talking about selling from business to business, or are we talking about selling from business to customer? So again, it depends on the solution which of these is going to be most important, but there's a wide range that are going to be of interest. So moving on, we just spoke initially about the data exploration and kind of the feature investigation. So I want to go on and talk a little bit more about some details that might crop up as we begin to kind of build out the solution. So the three kind of features, or kind of features of the model that I'm going to talk about, are kind of clustering, encoding, and then the particular algorithm choice. So there are various challenges around what each of these involves. So in generally, I guess now we're starting to talk about what algorithm we're actually going to choose after we've begun to accrue the features that were important to the price solution. So assuming that we're following a pretty kind of standard trajectory, so we're understanding initially what the problem type is it regression, time series, or so on? For a pricing solution, it's most likely to be the top two. It's going to be a regression of some kind, and it's going to have some time series involvement. There may be some classification, possibly, but it's most likely to be a time-based regression of some kind. We would then have done the feature exploration, which I touched on slightly, and now we're beginning to understand how we're going to take those features, encode them in a way that the algorithm we choose is going to understand it, and then move on from there. So as a pre-step, we may wish to consider segmenting our data set before we continue. So it's not necessarily always the case that you're going to have one model run over all of your data and it's going to provide all of the answers that you need for this particular business or this particular solution. It may be that it makes more sense to build a number of different models which are prioritized for a given segment or subset of the data. So say, for example, we have two features that describe our data set. It may not make sense to build one model for all of this. So the question is, how can we break up the data that we do have so we can apply submodels and see if that actually improves the overall performance across all of the data that we have? So as we begin to talk about segmentation or clustering, we have kind of two approaches. The first is to allow this to be data-driven. So we would apply an unsupervised method like k-means clustering. So here we have the example. We had generally two features spread out. We apply a k-means clustering, and then this has broken our data set up into various segments. And then we would apply a separate submodel to each of these segments and then test its performance. This has the benefit that it's data-driven. We don't need to really talk to anyone too much about this. And on the upside, the dense clusters that had a lot of data, they strip out the tails. These tend to perform better. However, the clusters that are now made up of the tails suffer from low statistics, and then they tend to fall away. So it depends what your priority is. If you want to achieve better accuracy or better performance in the core and ignore the tails, then you can use this to kind of cluster out and sub-select essentially what is of importance. So give an example of essentially a failure of this. Here we have two products, product A and product B, and say they're kind of defined, the model understands that they're different, but it hasn't deemed that their difference is too important, and it is giving a price. So we have a model price, this is the predicted price of a model, compared to the true price, what this thing was actually sold at. So we're doing a machine learning approach trying to learn from that sales data. So due to the loss optimization of this particular algorithm, it's decided that it's far better to just only focus on product B, which it performs relatively well on, and ignore product A, because this has actually achieved the minimum loss. And so if you just look at product A on the right-hand side, this has actually got a huge amount of bias, and it's effectively been ignored by the training of this because it wasn't deemed to be too important. But if we were able to split these two out and treat them with two different models, then this wouldn't occur. So in the example that we've split them out now the single product actually performs better than when it was left in combination with the previous one. So this aids us in the sense that we don't need to allow the feature exploration or the loss minimization of an algorithm to do everything for us. Right? We can break things out earlier and see if this aids us in some way. But there's two ways of doing this, and the approach that I gave, using k-means to select out subsets of the features that are going to particularly drive performance, isn't necessarily the best way, because the reason I gave was that the tails of the distribution are going to suffer, but we also have to remember that we're trying to build this for a business. They're going to use it. They're going to have to justify this price when they hand it on to someone else. The benefit of something being business driven is that it's understandable and it's explainable. So when you try and go back to someone and say, this is why it came up with this price, they can understand that it's been broken out according to something that they encouraged you to use. Oh, it's because it's sold in this region. It's because it's this product. It's because we're selling to this kind of customer. And that's also important when it goes back to the person who's trying to use that price as well, because when you buy something and you get given a price, you kind of want to know why the price has gone up this week. And you need to sort of make some sense, or you're going to lose trust in the business. So the second feature that we're going to talk about is the problem around categorical variables. So generally when we're talking about pricing solutions, as I said, we're talking about selling a thing which is described, it's a product, it's a service, and it's going to be sold into certain geographies, certain regions. So of the features that I spoke about at the beginning, a lot of them are going to be categorical in some form or another. So it's going to be, we're selling this type of product, it's this type of sales area, this type of customer. So it's not something that can be represented too easily as a number, it's kind of a categorical thing. And it can be challenging to introduce this as a feature into an algorithm that needs to learn from the importance of these features. So a given example, we had a problem recently, and if there were essentially 80,000 different values of a given categorical variable. So this is an extremely large number, and this needs to be dealt with in some way for any algorithm to understand how to use it. So we have a couple of options. The first is the simplest, I suppose, is one-hot encoding. So for every one of these values, we have a binary flag, yes, it is this, and everything else, it's not that. But bearing in mind the example I just gave you, if you've got 80,000 of these, this is an extremely large feature set that now you're trying to input into your algorithm of choice. Your second option, I suppose, is to just assign a numerical value to all of these. But then the question is, how do you decide on ordering? How do you decide which is number 1 and which is number 10,000? It isn't necessarily present itself as an easy solution. So what we found is particularly useful is to use a binary encoding. So what this does is it rapidly reduces the number of features that are going to be required to describe any given object if we describe it in a binary representation. So actually you end up with far, far fewer. And another benefit is you can introduce hierarchy. You can not just have a bunch of numbers that describe what the thing is, but you can begin to describe what's important about this product or this location. So a good example is location. So say we want to talk about describing a country, USA or UK. How do you describe like the Americanness of America, right? But it means something, and it can be, and it needs to be kind of, it needs to mean that and express what that is when your given algorithm begins to try and train for this and learn what's important about this feature. So as an example, say what's important when we're using a country is wealth. We want to describe GDP, for example. So if we were to order the USA and the UK by gross GDP, then you have the USA as first and UK currently sixth. And if we encoded this in a binary encoding, then we'd end up with, say, 3 or 4 bits, and then each bit would describe where this particular country sat in the hierarchy of GDP. So for the USA, only the first bit is enabled and everything else is set to 0. But for the UK, the second and third bits are enabled, and then each of these carries information in itself, because each further bit that we move down this list, even if the algorithm only looks at that one feature, this means something because it's telling you that this country is moving further and further down the list and is becoming less and less relevant for this particular item of interest. At the same time, all of these combined don't just express GDP, they express the location of the country itself. So this is, we found that actually in combination of massively reducing the number of features that are required, it actually introduces a lot more information as well. Okay, so I've spoken a little bit about the features that we're beginning to explore and then how we're going to kind of compress these or encode these in a way that are going to be useful to our algorithm of choice. For pricing solutions, I mean, you have a wide range of options, but what we have found and what we've used kind of spread across a number of options. So depending really how dominant the time series aspect of a pricing solution is, tends to kind of justify which direction we end up going with in terms of choosing the algorithm. So if it's a particularly static pricing solution, we might choose for a decision tree of some kind, boosted decision tree, random forest, something that's going to be very useful when we've got a large number of categorical variables. If the features are more uniform and we're not dealing so much with various splits of different types of feature, we may want to use an artificial neural network of some kind. Or if the time series aspect of it is more important, if it's a simple time series, we might be applying an ARIMA model of some kind, and this might be useful, for example, in forecasting future demand on a relatively simple project. But if it's a more complex based time series, then we would tend to use something like a recurrent neural network. And I'll give an example a little bit later about when we've needed to apply a recurrent neural network to help us out. Okay, so moving on. So we've spoken a little bit about, started with the data exploration, added in a few bits, things that were interesting at some point in various projects, the clustering, the encoding, and the algorithms. So let's say now we've got something we're going to actually try and use. We're going to think about testing it and seeing what problems we encounter. So 2 of the problems that we've encountered and I'd like to share a little bit about is just general optimization when executing a model, and then adapting to things that were not visible at the time that the model was actually trained and first tested. So on code optimization, we can kind of have a couple of assumptions, things that tend to crop up a lot, or that I think I in particular notice as a broad sweeping description of the kind of landscape of data science. We have kind of over the years a lot of transition from very bespoke use of compiled languages to interpreted languages, and increasing numbers of wrappers around libraries that make things extremely easy to use. So you can have a notebook few lines of code, and this gives you a deep learning model. Like, it's extremely fast to develop. But underlying that could be thousands of lines and many, many years of development that you no longer really have access to. I mean, it's kind of a trade out of that. The second is something that we've noticed, perhaps as a kind of an admission of guilt in some way, is that sometimes development speed is prioritized at the expense of the execution speed in the end. So, like, how efficient is this solution going to be when it's actually productionized? And are we thinking about that right now? So it's kind of a POC mentality. Everything is focused on, can I get a quick answer out in the next 2 weeks and present that? It's just a notebook, it's just a few scripts and a few plots, and that's what I'm focusing on, without perhaps extrapolating to how this model is going to run in the live and how it's going to perform in the real world. Because the production deployments might be very different to when you're running on your laptop or when you're running on a virtual machine. You might actually require much higher frequencies, low latencies. There might be considerably larger amounts of data that needs to be considered. And the way that we find we develop things from a POC doesn't necessarily always translate that well into a production solution. And then the final consideration is that compute has gotten cheap. Right? There's huge access to cloud resources, libraries that will allow you to use various parallelization paradigms, and this is ubiquitous and it's easy and it's almost always available to you when you begin to do your investigation. So in terms of the optimization and the various things that we've considered at certain times on different projects, is you kind of have a hierarchy going down. So you might start out with the high-level parallelization that I talked about, so using Spark, using Databricks. I mean, it has its upsides and its downsides. So one, I mean, it's expensive in cost. It's expensive in expertise as well. You need to have people who are capable of creating this cloud architecture to serve your needs. But it's kind of infinitely, if you like, scalable to your volume of data. So in one sense, I think the things that we've learned is this is a viable option, but in some sense it should be the last option. Right? When you've done everything you can, but your data volumes are so large that this is where you have to go to. The second option is local parallelization. Not everything is necessarily optimized to use the number of cores that you have on your machine. This is kind of a switch between using local parallelization and kind of the high-level stuff, but in development, it's always perhaps an option to aid in the short term. The third that I found actually pretty useful recently is that you don't always have to use the libraries that are available. So often implementing something in the pure language, the standard library, can create efficiencies for you that would not have been there if you're using the overhead of kind of a third-party library. But this has its downsides because you're beginning to create more and more bespoke code that isn't necessarily transferable or understandable to someone who might come along and pick up the same thing. Right? It becomes a documentation burden. The fourth, which is particularly interesting from my point of view, is we have this general assumption that we're using an interpreted language of some kind, right? Probably Python or something else, but that comes with its own costs in terms of development. So it is an option at some point to use a compiled language in place of certain parts of the interpreted language. So there may be instances, at least that we have found, where applying a Python function to something hasn't necessarily been the best option because of certain considerations. And just by taking that particular section of the code, mapping it out into a compiled language like C++ increases the performance enormously. And I just give a couple of examples. These are real examples of a couple of functions that we had on a project. So something that was taking 3 hours, 20 hours, 2 days in the best kind of optimized Python that we had. If this was just written in bespoke compiled language like C++, the execution speed of this function increases dramatically. And this can be implemented in a number of ways. It might be Cython. It might be just externally executing an application that's been written in C++, or it might actually be creating a new library to extend an interpreted language like Python. And then the final thing, which is often overlooked, is just good algorithm design. And I think, again, because of the POC mentality, you want to type as fast as possible and things aren't always thought about. So, well, I'm talking about myself and I'm kind of admission here, but I find that the first thing can actually mitigate everything else. So the second fix, just as an example, that I want to touch on is getting back to the model itself, is how we deal with changes in the market or changes in what's happening to the business after we've done our model development and after we've trained and produced something. So say we have had a static amount of data that we've trained our model on and then we've executed it. There's a possibility that the performance of that model is going to drift over time. So this is likely or possibly due to any deviations in the market that weren't visible at the time that you trained your model. So you may have done the best job possible to train and test and validate what you had, but after you release the model, things change, the market looks completely different, and now you're not actually achieving the same performance that you thought you were going to achieve. So how can we deal with this? We can try and make the model more time dependent, make it more of a time series to see if we can actually accommodate these fluctuations over time. But if the majority of these features aren't time dependent, then it's kind of a difficult compromise to switch from using a pure time series like solution to something that's not so much. So what we found can be useful is to have a static model, a static regression, which is trained on our historical data, producing the best price it can according to that historical data, but then to overlay a time series on top of that. So we have a static price that's predicted, and then we have a time series which is continually learning from changes in the market, which then scales that predicted price up or down. So you can kind of have a range of options. The simplest of these would just be to track over time what is your model predicting and what should it have predicted. So this is the case that we still have sales data available and we're still kind of learning from that sales data. So at every price that we predict, every kind of sale or quote that's given, we have what our model predicted and we have what it was actually sold at, and we can see the difference. So the simplest option is just to compare those differences and then scale and forecast that difference in the short term and scale accordingly. So applying a rolling average, exponential rolling average, something like that. And that does okay, but it doesn't free you from being trapped into using that data, right? Ultimately, for a pricing solution, you want to move away from being dependent on the data of the business so that the solution can stand on its own. So a more complex approach would be to use a recurrent neural network. So here's an example of using long short-term memory. So what we did here was we stripped out the actual prices that the thing was actually being sold at, and the only inputs into this LSTM were other market factors which were always going to be present. How much did the business sell? What was the total revenue? What was the total sold in the market? And things like this. And these are the inputs into the LSTM, but what it's predicting is the difference between what the static regression model is predicting and what it should be. So it's kind of predicting the error on our original model. And if you can see that on the top right here, the red points are the actual fluctuation day to day between the static regression model and what it should have been pricing at. It goes up or down 5-10% bias. And then the green is the forecast of what the LSTM thinks the error is going to be. So if we compensate between the two, which is the plot at the bottom here, the red is the actual error of the static model, the blue is the prediction of what we think the error is going to be, and then the green is the corrected factor. So what it allows is to have the static prediction from the regression, and then have this edited or scaled day to day, and it brings it back in line so that we're kind of maintaining a relatively central distribution with low bias moving forward. So I think we're going to stop here for a little bit, as I've been speaking for 35 minutes. So we're going to break, and then we can have some discussion. We can answer some questions about anything that's come up in the last sort of section of the slides. Does anybody have any questions? Yeah.
When you split up in submodels,
yeah.
How many of them do you have done?
That depends on the solution, because we're talking about sort of different things. The example I gave, there may have been 10, but we have other solutions where it could be into the hundreds. Yeah. So that means that you're running hundreds of submodels in parallel, and so when this comes to be executed, you have a kind of an interface layer. So the request for the price comes in and says, all right, which model should this be applying to? Look that up, make that prediction, and send that back. So it becomes when it goes into production, there's layers that have to be kind of wrapped around it. Yeah.
So the models that you create, like where do you factor in your goal of optimizing on revenue or probably the market share? So where does that come in the picture?
So the question was, I forgot, I should have repeated the question. The question was, where does the ultimate revenue or how does that come into the training or the yeah. So the examples that has been speaking so far is that kind of first phase, which was standardizing. So we're kind of learning what the price is now and replicating that and trying to have some standard response. So that revenue, so in the price itself, rather than like any profit perhaps, is the Y, right? That's the output value of the model. So the error on that is what we're kind of training for. Sorry.
How do you go around collecting information about price elasticity for firms that don't hold that information in-house?
Okay, so the question was how do we get price elasticity for firms that don't have that? That's the second section of the talk, so I'll get to that. Sorry.
Did you experiment with embeddings for high knowledge features?
Not as such. It's an option. Yeah, so the question was, have we experimented with embedding layers? Not for these solutions, but yeah, it's certainly something to think about.
Just to clarify, the bit you've been describing here is you're trying to predict, you're trying to just recreate the existing pricing process.
Yeah.
Is that right? Rather than, and with the purpose of automating that? Is that right?
Sure.
I'll just give David a little bit of a rest. So the first step, and it's quite typical step, right? You're trying to make your client comfortable first, right? You want to reproduce essentially best practices. Sound good. Yeah, so you're trying to kind of model their best practices, and depending on what you're trying to help is, right? If you're optimizing prices in the supermarket, that's maybe not an issue, right? But if you're talking about large organization where there is a lot of salespeople who are actually still participating in the process, the issue is that, say, a lot of sales force, they're not necessarily as experienced as their best salespeople, right? And the prices go all over the place, right? So there is kind of double benefit in first modeling what they currently do. One benefit is, well, you're making the client comfortable, and the second benefit on the way there, you can also kind of emphasize modeling of the more expert sales team members rather than everybody. That's a typical first step, and then the optimization, say, is what David will be talking in the second part of the talk, is the next step, right? So once you convince that you actually the client, that you understand them well, understand the sales process well, and can help them, to take these outliers from the bottom and bring them to the best practices, then as a next step, you can talk about optimization and further pushing the bottom line up. Yeah.
Standardizing and automating.
Yeah. Yeah.
Question to follow up on that. So you're predicting at the end the price?
Yeah, so for this solution, when we're talking about price optimization, yes, we are talking about predicting the price. Then for the next stage, when we are talking about optimization, we can discuss optimization against revenue, against specific target, not just modeling the prices, but optimizing for larger revenue or larger market share.
Do you include the volume in place? So, for example, because I guess that would be related as well to the second part, but if I would increase the price 100%, then probably people will
Yep.
not buy my product as much.
Yeah,
So
absolutely. That's exactly the consideration, right? And the business can have different goals in mind. And there are but more considerations still, right? It's not just whether you will lose the part of market share if you're trying to optimize, increase the price, which is actually not always necessarily a bad thing, right? So you may not be kind of having as much of market share, but that the market share which you will have is a better focused kind of group of clients, so to speak, right? But there are even further considerations, right? For example, if you're an established business, it's not even necessarily about money or volume. It can be about even relationships, as in human relationships of that company, of those salespeople with their clients, right? So, and they may, if you start optimizing price against them, they can say, well, I used to buy you of this product from you for price X, and now you are proposing that I buy it for X plus delta or whatever, right? So you may lose them even for that reason, right? So there are further layers still, in addition to the consideration of the market share versus bottom line revenue and things like that. But business may have different goals. They won't necessarily want a larger share of the market. They may want to have more focused part of the market for a higher price, selling for a higher price.
Is there any way we could go to see code examples of this kind of technique of layering the base model with a time series sensitive one?
Well, we can't disclose the code for the client.
I mean, just maybe a book where you think this has been described at a code level?
I'm sure there are some books. The idea behind the correction factor is relatively straightforward, right? And that's why we didn't necessarily base it on some books or some articles, but kind of built a bespoke solution for that, right? So we effectively, and we have multiple kind of layers of the correction of the price. So we have the short-term correction, in particular examples which David is speaking. So your model, because it's quite inert, right? It's based on the training of several weeks or even months or even years, right? It wouldn't necessarily catch up with short-term fluctuations, as in something happened with your competitor and you can allow yourself to increase prices by 10% in the next 2 weeks until a competitor fixes whatever problem they had, right? This kind of short-term correction you have to do on an ad hoc basis, and that the correction what we are talking about. And this correction you're simply studying when you're modeling the best practices. You're simply looking at the difference in the prices, actual prices versus what your model was predicting, right? And this happens in the live test, as in the agents, the salespeople say, producing some prices, and they know that they can push because there is a problem on the competitor side, and your model doesn't know that yet. And this correction factor is simply looking at this difference, and it can be, of course, rolling average, which is also weighted by, proximity to the event which you're trying to correct for. That's all there is to it if you're talking about short-term correction, and you can play with it depending on the business you're trying to optimize, just from these kind of core principles. I'm sure there are some interesting articles with more complex mathematics behind it as well, and maybe even established libraries in Python or R for that as well.
So what you mean is you could basically just have a rule
Yep.
that sits around the model predictions
Yep.
based on some external information
Yep.
that could shift the suggestion
Yep,
up or down.
exactly, yeah.
Should we? Yeah, do one more.
Do you want to continue? Yeah.
One more and then you'll.
How do you deal with product catalogs which have like attribute-based SKUs? A SKU would be, say, a business card, but then there's 10,000 different variants which could be created from that one SKU. And then the way it's being priced has been using a full set price of saying, yeah, you order at this volume, it's price A, you order at this volume, it's price B.
So you're talking about is the question how you would deal with discounting kind of, or?
Well, it's discounting, but it's also basically you don't know what variant of the product's going to be ordered before it's ordered. So you create one stock item, but then you have multiple different variants of that one stock item, and then you've got to price it in a way that incorporates all those different variants.
Okay, so the question was how would you essentially like algorithmically price something which was on the face of it a generic product but had various kind of post hoc changes to it that would change the price?
Yeah, so for example, sizing might be
Yeah.
an issue. So like if you stock item is a t-shirt, then you might have the child size of that t-shirt selling at a lower price than the XXL.
Yeah. So it's not something we've in that sense come across, but
You would need to fold in demand forecasting into this model. That's what you're talking about, right? So you as part of this pricing engine, you need a comprehensive demand forecasting as part of your model, as well as the whole separate step for that, right?
And that's, I guess that's our issue. Our issue is we've got sparse data on the actual demand.
Yep. Well, then, as the classical answer goes, it depends, right? So then we need to look at the case, how sparse is the data, if we can do clustering of any of it, if we can fill in the gaps, and
okay. Okay, so I'll kind of press on, and we can have some more questions at the end. So in a sense, we've kind of gone through various tangents about processes along the way for coming up with a given solution, and now I want to get on and talk a little bit about what we do with that solution in terms of actually productionizing it and providing it as something that people are going to be able to consume. So in general, at Altius we use a great deal of Microsoft Azure based infrastructure, and that's sort of pretty much what I will be describing. But of course, other cloud service providers are available. So in terms of production and deployment, the example I'm going to give is for something that's like a very dynamic price. So it's something that we're going to be recommending a price for on the fly. So instead of calculating a bunch of prices overnight and then kind of giving it out as you might expect in, say, a shop store, but something that's going to be more online, where the price could be changing with a great frequency, and so it's going to be calculated dynamically. So typically we kind of see this in a cloud infrastructure, and what we would be looking at is that a request for a price comes in. So like I said, that could be just an API that we provide, or it could be a web front end that's been designed as well. But ultimately a request is going to come in. So this then would come into to a layer that's going to handle this request and then distribute it across to the models themselves. So the models, typically we would deploy these in Kubernetes. So each instance of the model is going to exist in a pod in a Kubernetes cluster. And then when the request for the price comes in, a load balancer is going to decide which of these pods is available to generate a price, and then ask that particular instance of the model what the price is. That will then be wrapped up and returned. And this is generally wrapped in kind of a Flask app, so that a request comes in from an API endpoint, that price is calculated and then returned back out effectively the same way. So the benefit of this is that it's extendable, and the load balancer is going to make sure that we're always kind of pointing the requests towards an instance of the model that is available to calculate that. So it takes some of the burden off. It doesn't necessarily limit the issue of how fast can your model itself come up with a price. That still needs to be optimized, but it helps a great deal in terms of if you had a large number of concurrent requests. So this is the execution itself. So each of these worker nodes may have an instance of the model and is kind of returning a price based on that. But we also want to wrap the entire process of building the model into a cloud infrastructure so that it's sustainable. It's no longer dependent on a data scientist having to kind of open their laptop and train the model and then like send it somewhere. All of that, every kind of part of it needs to be moved into a cloud infrastructure and architecture.
Check
so
1
that
2.
has a great amount of redundancy and reliability. So we also have a separate aspect which is involved with training the model and also calculating that kind of ad hoc scale that we've been discussing as well. So for this, you're depending on a lot more data. So it's not just one request coming in which you calculate the answer to and send out. All of the data feeds that are required to train the model and also to execute the scaling layer, the kind of time series that's fitting on top as well. So generally we would have all of the data feeds coming into some landing zone. These would then be passed through various layers that undertake general data engineering. So we're going to be kind of checking for consistency. Is the data that we've been sent really what we're expecting? Is it in the right format? Is it complete? And so we have various layers in the data lake which will check for each of these. And then we can use some established technology to kind of run each of these layers. So the example we give here is Databricks. So as each of these data feeds comes in, it's passed to Databricks to execute each of these checks. Is the formats correct? And then it moves down each of the layers until finally it ends in a format which is ready for ingestion into the model. So that by the time we get to prepared, all of the unnecessary data has been stripped out. It has been reformatted in a way that the code that executes the training of the model can ingest it immediately. So everything from the first data feeds through to the execution of the model is kind of prepared in this way. And then finally, the execution of the training of the model itself is itself distributed in a Kubernetes cluster so that we can manage the resources that are required to train this depending on the frequency at which the model needs to be retrained. So it may be monthly, weekly, or it may even be a much higher frequency than that. And the structure of the kind of the Kubernetes resources will be scaled according to how sort of the requirements of retraining itself. So this is sort of generally the kind of key components that we're talking about. An API endpoint, a model wrapped in a Flask app, which is containerized in Kubernetes, and then behind that, a data pipeline, which also has the training of the model also in Kubernetes, supplying the model to be executed in each of those worker pods. So once we've kind of wrapped up our model and then we're kind of putting it out there, we have an element of risk in the sense that we've now become responsible for a business's prices. And ensuring that the price is going to be good or reliable or accurate becomes of concern. So we need to come up with a metric of, at the time we give a price, also giving our confidence in that price. So we don't just give a price, but you also need to say like, yes, this is an accurate price, or actually maybe this isn't so accurate and we need to do something about it, or maybe not actually use it. So we can do this by learning from the test sets, or a separated test set of our data. So say we've trained on the historical data, we've made predictions of what that price could be, or what the price should be, and then we've compared from the test set of what the predicted price is and what it was actually priced at. And so we can have a distribution here on the bottom right which shows the difference between what was predicted and what it was actually sold at. So you have a little percentage difference. We then want to break this down into two regions. One which is your sort of good pricing, and we've said, for example, that's within 5%, and then not so good pricing, which is something which was more than 30% away from what something was actually originally sold at from the test set. We then want to see how this breaks down at the feature level and at the value of the feature level. So here, this example could be one particular categorical feature, and then running along the x-axis is each of the values of that feature. So for each value of that feature in the test data set, we can calculate what was the accuracy for all of the bookings that had this value of this feature. And then we begin to build up a picture of what it looks like for each value of every feature, the accuracy. So when a new price comes in that isn't from the test set, it's a live pricing, we can then look up from these tables what the accuracy of each value of each feature was. And then we're going to combine these together in some way. And there's kind of various ways we can think about combining them. But ultimately, we'll be looking at, for feature A, and the value we have for feature A, what was the accuracy from the test set, and then continue this for each value of each feature, and then combine these together to come up with the confidence, and then we return that with the price to say, well, because it was this value of this feature and that value of that feature, we're really confident historically that we can price this particularly well. So this is returned and then can be dealt with accordingly depending on whatever kind of solution design the businesses have. Okay, so finally we can get on and actually talk about some of the optimization methods that we've been working on. In particular, I'd like to focus on how to optimize without data. This goes back to the question about price elasticity when you don't know what the elasticity of a given business is. So kind of moving away from that standardized approach where we're just trying to replicate what the sales structure or the sales strategy has been in the past and come up with a new price which is different perhaps to what the business has been using in the past, but it should be a better price depending on what strategy they want to employ, right? Increase revenue or increase market share. But it's quite common across a lot of industries for not to have elasticity. So what I mean is people may be recording the things they've sold, but they're not actually recording where they've lost business, where they could have sold something, but they didn't because the price was too high. This could either just be by design, if you like. So a high street store is a good example. When someone wanders in, has a look around and walks out, how do they really know if it was because the price was too high or anything like that? But it also could be because the systems that the business had in place weren't actually capturing the data when they could have been. So there's a couple of things we can begin to look at when that data doesn't exist. The first option is just the old way, come up with a theory and then apply it, and then that's it. But some of the options that we've looked at are to adjust the loss function when you begin to train a given model. We can infer price elasticity based on the data that we do have. We could learn from expertise, and that's something that we have considered. Or we could begin to prepare for when we do have that data and actually test hypotheses around what the elasticity would look like by generating simulated data. So as far as adjusting the loss function is concerned, when an algorithm like a decision tree or a boosted decision tree trains, is trying to minimize the deviation between what it's kind of estimating the price should be and what it actually is. And generally that will be like mean squared error or absolute median or something like that. But you also have the option to adjust the loss so it favors a higher or a lower price. So the example we have here is that you might have the black line, which is just trying to optimize for the median price, but the red or the green may be optimizing for the lower or the upper quantiles. So this gives a range of prices. Now you could have something which was the red band, which is based on the historical data. This is typically the lower 25%, and now we're lowering the price to increase sales. Or we could say based on the historical data, we want to optimize for the upper 25%. This is the green band. Now we're increasing the price. So this works particularly well if you have a model which is well performing, so it's quite accurate, and you just want to get a few percent edge. You don't necessarily want to worry about probability of winning, but you know you're replicating the prices well, and you just want to turn it up 5%. So this is a kind of an intelligent way of doing that. So rather than just taking all prices and kicking them up 5%, you're now looking at the historical data and seeing how each individual product historically was priced, and then pricing it just a little bit higher based on what you've seen. The second option is about interpreting elasticity. So it's if we are concerned about knowing when we're going to lose business, the probability of losing business for a given sale, then elasticity becomes important. So if we have some true elasticity, so we have the probability of making a sale versus price, and it's the probability that you're actually going to sell something decreases with price. And if we knew this absolutely, then we could put our price somewhere on this curve. Right? We knew how much risk we wanted to take, and then we could place it somewhere on that curve. But if we don't know when we're losing the business, then we can't actually know what this curve looks like. But what you do have is sales, and you can see how the number of sales for a given project is decreasing with the price. And then somewhere at the end of this is where the lost business is occurring. It may not be in the same place, but it's sort of as the sales tail off, that's when the lost business is beginning to increase. So we can kind of follow a similar approach to what we were discussing around the confidence. So we can just look at the historical data and then say for every feature, and again every value of every feature, how did the number of sales for this value of this feature decrease with price? So now we've got distributions for every value of every feature, and then we can see how things fall off when the price goes up. And again, for a new product, we can then combine all of these together. Take the product, we take some kind of sum and apply an activation function. I mean, there are many options, but we combine them all together, and now we have a distribution for a given product, a given single example of what we're trying to sell. And then based on the historical data, we can see how for this type of thing, how did the sales fall off with price? So this is kind of a data-driven but also extrapolated price elasticity. Now, when we have new test data come in, we can, for this given product, we can actually start recording when we do sell it and when we don't sell it, and then we see where these sales and these lost opportunities fit in our curve, and then based where we kind of fall off on that curve, that's how we know when the elasticity is kicking in and we're kind of reaching that limit of how high we can actually price. So this is quite useful when you just have no access to lost sales data. So for example, in a high street store, you have no idea why someone's walking out, but you do see how sales of a given item decrease depending on how high the price has been. And the final step is really about preparing for when we do have the data around when a product is lost due to the high price. So often this can take quite a long amount of time. So if we first engage with the business, encourage them to begin to start accruing this data, but that may take years in a sense. So we need to think of a way to prepare for that, but also to see if we can learn anything as a result. So we can simulate data. So we can look at the cells that we already have, and then based on the distribution of the features and the values of the sales data we do have, we can come up with some PDFs of this kind of distribution, and then we can generate pseudo booking, pseudo quotes, pseudo sales of some kind. Right? At the same time, we can come up with various theoretical or hypothetical assumptions of what a market is and what price elasticity looks like. And because we're simulating this, we can come up with any number of hypothetical combinations of what elasticity in the market looks like. And then we can apply our data that we've generated from the real sales onto our hypothetical market elasticity and see what happens. So now we're generating pseudo or fake wins and losses. And then from this, we can then begin to train our algorithms and then test what kind of algorithms we're using. So we're doing the whole kind of train and test pipeline, but on data that we've generated ourselves under different scenarios. So why kind of waste your time? Because we are generating market elasticity from a whole bunch of different scenarios, we can build robust models. We can build a model that no matter what happens in the future, when we do have this data, we're ready for it because we've tried all of these hypothetical scenarios. It also allows to forecast how much data you're going to need. Because you're running this kind of simulated training and you're testing the accuracy on that simulated model, you can forecast how much data is going to be necessary when that real price elasticity data comes along, and then you can plan accordingly how long it's going to take to build out the solution. So ultimately, what this would look like is that you would have kind of data that's going to follow some kind of distribution. So for a given feature, as the feature increases, we're going to have some number of sales and some number of losses. And then the final aim of an optimization algorithm is to kind of find the barrier between these two. So either we're talking about finding a borderline using an SVM of some sort or some sort of similar algorithm, or we're talking about trying to fit what that price elasticity is, and then once we know what price elasticity is, we can then kind of come up with a price. Because ultimately, the revenue is going to be the price that we give times the probability that we're actually going to win with that price. So the final thing I want to get to is we just kind of described how we would apply a kind of production solution, but that isn't really the end of it. So once you've kind of built something and trained it, and it's existing in the cloud, and the training is automated, the execution is automated, and the data scientists can kind of retire, it still has to work, right? It still has to kind of keep running, and someone's still going to be using it. So we can think of that as kind of an operations phase. So at each release, kind of the R&D ends, it's been productionized, it's been released, and now it needs to be taken care of in some way. So, and it needs to be maintained for whatever the lifetime of that product or service is going to be. So from our experience, there's some prerequisites. I mean, you've got to have a stable deployment architecture. So this could be on premises, or it could be in the cloud. The cloud is perhaps a better option for a redundancy. You need to have integrated monitoring of the input data. So when I mentioned earlier about this automated training feed, the data that's necessary for the training was coming in, that's got to be monitored, because that might change. Someone might change their SQL query somewhere and then give you a bunch of junk. You need to kind of be monitoring this and making sure that you kind of have an eye on it, and that needs to be integrated into the cloud solution, or whatever the solution is. Similarly, the performance of the model needs to be monitored. So how accurate is the prices that it's generating? Like, what is the revenue? Is it driving revenue? Is it actually causing losses? All of this needs to be monitored in the same vein. And then there needs to be kind of an alarm system wrapped around this, so that if the input data is not as expected, that triggers an alarm. If the price is going too high and you're losing business, that triggers an alarm. And then the result is kind of a ticketed system. So if it's a data problem, they might go to a data engineer, could chase up those feeds. If the price has been drifting over time due to no foreseeable reason, then it may need to go back to data science, and then we kind of have another R&D and research phase. And in general, kind of just applying key kind of DevOps structure. So we kind of have continuous integration, like I said, and then continuous delivery and deployment, which kind of summarizes overall what I've been talking about. And then for the architecture itself, what I gave was just one example, but really we would have, say, 3 or 4 copies of this for development, for local testing, for acceptance testing by whoever is going to be responsible for this, and then the final production architecture as well. So I'm somewhat coming to the end, but I'm very mindful, or we're mindful that we didn't talk about quite a lot of things, which we can certainly talk about if we have some more discussion. So it didn't even get to that final point, which was about reinforcement learning. So this is where we're talking about a pricing agent that is no longer learning from anything that has gone in the past, and it's exploring what possible prices it can get on its own. And how this would actually factor into the reward system that we spoke about at the first. How is this reinforcement learning agent actually going to achieve those priorities? I only talked about live productionization. There are other kind of needs that things may be run in batch. So there are other ways to structure this. And also, there's a lot to talk about how you actually test this. So we're not just talking about testing the data in your development, but once you've built a production solution, the business is going to want to use this. How do you test that with minimal risk to the business? So we talk about kind of A/B testing, talking about small trial live testing periods. And then we also have processes where even if we're only operating in the live environment on a small subset of prices, we want to be running offline in the background on all possible prices. So we call this shadow testing. So we're monitoring how we would have been doing had it actually been deployed to a full, kind of across the full market. So in summary, kind of gone around a couple of general things that we have learned across the pricing solutions that we've built through. So various challenges around encoding and how we would actually kind of build out these types of features. Commented a little on optimization. Adapting to the market, so we have that single solution and then we're trying to put a time series on over the top, describing some of our productionization methods in the cloud, and then also the elasticity, so we touched on how that would kind of be achieved in the absence of real data and how we would prepare for the arrival of real price elasticity data to provide an optimized solution. And I finished up talking about how we would monitor this for the foreseeable future. So I think we can get on to, thank you for your time, and we'll have some more questions.